We have all heard that the universe is expanding at an increasing rate, but is this actually true, or is it an illusion caused by time actually slowing down? We are going to get into the weird world of dark matter, relative time, and fabric stitching. That's right, you heard me correctly. Today on Into the Multiverse.
This is Into the Multiverse with Josh Peck.
Welcome to Into the Multiverse. I am your host, Josh Peck. Glad to be talking with you again today. I've actually been wanting to cover this topic for a while and really just haven't had a whole lot of time to deal with it properly because there's a lot of different avenues in this thinking that we're going to look at. If you haven't had a chance to, make sure you subscribe to this channel and click the bell for notifications. If YouTube doesn't notify you, that's okay. Just know that every Thursday morning at 9 a.m. Central, you will get a new Into the Multiverse. So the last time we did more of a long-form show like this, a long-form episode, we got a lot of positive feedback, so I have decided to continue in that format. The way we have it set up right now, you're going to get a longer episode. You know, it's going to be longer than the typical 10 to 15-minute episodes that we've been doing. You'll get a longer episode, and then we're going to try to make it every day where you get a clip from that episode after the episode airs. So many of you have probably realized last week you got a lot of daily clips from the interview or from the episode before. So that's what we're going to try doing. People seem to like it. I seem to like it. So we'll continue in that fashion. All right. So I want to start off with how exactly should we think about time and the universe expanding? You know, there was a really interesting question that I've grappled with: old Earth versus young Earth. You know, and usually they say old Earth or young Earth, but typically it's old universe or young universe. There's a lot of interesting arguments on both sides of that topic, but one that I haven't really heard yet, and we're going to get a little bit into it today, is if time itself is relative, and it is, and we'll look at that in just a minute, how do we know both aren't true? How do we know it's not both young and old, depending on your perspective? Now, I know that seems weird because it seems like that these two ideas contradict, but surprisingly, they actually don't. So we're going to get into that. What I really want to look at, though, is the actual expansion of the universe. Is the universe expanding at an increasing rate, or is this just an illusion because time itself might be slowing down? So really, really interesting stuff. I want to start with this article. This is actually something that I wrote a few years ago. I'm going to be updating this. I'm going to be updating this and posting it to my website, dailyrenegade.com. So this is a few years old. It does need some updating. Whatever I notice while we're going through this that needs to be updated, I'll tell you about. But I think this is a good springboard to all the rest of the stuff that we're going to talk about today. So it says that. So again, I wrote this a few years ago. The Earth rotates a little more than 1,000 miles an hour. It revolves around the sun at an impressive speed of 67 miles an hour, or 67,000 miles an hour. The sun, along with the solar system, flies around the galaxy at 483,000 miles an hour. The Milky Way galaxy moves through the universe at an incredible 1.3 million miles an hour. The interesting thing is, movement and speed have a direct effect on time itself. Now, I say speed. I probably should have said velocity. That's probably the more accurate term for this. But basically, for our purposes here, it's the same thing, so it doesn't matter. Albert Einstein was able to show how time can be different for an individual depending on the speed with which he is moving. I discussed this in length with Dr. Ronald Mallett in my book, Quantum Creation. And actually, Quantum Creation was updated and expanded to the book Unraveling the Multiverse. So if you want the completely updated version of this, that's the newest possible information available for this, check out Unraveling the Multiverse. You can find that at skywatchtvstore.com. And the cool thing, too, is Dr. Mallett, at the time of this recording, I reached out to him today and asked him to come on Into the Multiverse for an interview for a future episode, and he said that he would. His specialty is in time and black holes, time travel, that kind of stuff. So one of these days, we're going to do an episode on gravity, black holes, effect on time, and we'll bring on Dr. Mallett for an interview for this show. So that'll be exciting. Look forward to that. But in the book, book, I interviewed him, and again, the book is Unraveling the Multiverse. Quantum Creation was my first self-titled book. So Quantum Creation and Cherubim Chariots, another book I did, I combined those and updated all the information to make Unraveling the Multiverse, which was published through Defender Publishing, and again, available at skywatchtvstore.com. But I kept this interview in there because it was a great interview. Dr. Mallet is absolutely brilliant. He's a Christian, by the way, too, which is interesting. But here's what he had to say. He said, quote, Einstein had developed two theories. One theory was called the special theory of relativity, which he developed in 1905. That theory, in a nutshell, says that time can be changed by motion. All right, so keep that in mind. It's not going to let me highlight that, is it? Well, just from here, that theory, in a nutshell, says that time can be changed by motion. Keep that in mind throughout today's episode. That is to say, the faster an object moves, the more time will slow down for that object. Now, another way that we could look at this is the faster time will move outside of that object. So the faster you move, when you finally stop moving, the more time you'll realize has actually passed in the universe around you. So it might only feel like 5 minutes to you, but it could be 5 years on Earth. So really strange. Continuing on. Time for a moving clock will actually slow down. That's essentially the essence of Einstein's special theory of relativity. It turns out there are experiments that have been done that actually show that time can be slowed down. In fact, one that most people don't know about was done in 1971 at the Naval Observatory. What they did was take two atomic clocks. One of the clocks was kept at rest at the Naval Observatory, and the other was put on a moving plane. The plane was traveling close to the speed of sound, and when they brought the plane back, they found that the clock had been on the plane had actually slowed down. Now, it was only by fractions of a second, but it did show exactly what Einstein predicted. Time slows down. The effect becomes greater the faster you move. The closer to the speed of light, it's not just in terms of fractions of seconds, but in terms of hours. In fact, there's a device called the Large Hadron Collider at CERN in Geneva, Switzerland. They have subatomic particles that they can accelerate close to the speed of light. Some of these particles normally only live for a millionth of a second. What they can do is, by accelerating these particles close to the speed of light, they cause these particles to live 10 times longer than they normally would. Now, that's really interesting because to the particle, if the particle had consciousness, to the particle would feel like time was going by normally, second by second. But to the outside world who's observing this particle, it's actually a lot longer. It can be hours. It can be a lot longer. Isn't that strange? So this happens regularly at particle colliders. Continuing on, remember too, when I'm talking about a clock, I'm not talking about a mechanical mechanism. Your heart is a clock. That means your heart would slow down. You would actually age less than other people. This means if you were traveling fast enough for you, time might only be a few years, but if you were moving fast enough, decades could be passing for everyone else. You could wind up literally in the future only being a few years older, whereas here on Earth, decades have passed. So that's essentially time travel into the future. And that's absolutely right. So we've talked about that before. Time travel has been proven, but only time travel into the future. That can happen. You just need to travel very, very fast. So as I wrote in the article, the faster we travel, the less time will affect us and the more time will pass for everything else. So basically, speed affects time. Now, given the fact that we are constantly moving in the universe, this begs the question, is our time being altered? In other words, what we think of as the normal passage of time might not be normal at all. And this is why time itself is relative, because it depends how fast you're moving, and everything travels at different speeds. So time on Earth is going to be a little bit different than time on Saturn. Another thing, too, is gravity affects time. So time near a black hole is going to be very different than time here on Earth. What I really tried to look at in this article, and what I try to explain when talking about this, is what if the only reason we even experience time the way we do is because we're moving through the universe? The Earth is rotating around the sun. Our solar system is rotating through our galaxy. Our galaxy is moving through the universe. And possibly our universe is moving through four-dimensional space as well. So all of that movement affects time. What if that's all time is? What if that's why velocity and time are linked in that way? And in that way, could time and space really be the same sort of thing? Is time really just another kind of space? So it's really weird. It's really weird to think about that. Our whole idea of time might be wrong, and this does factor into the expansion of the universe. Before we get there, though, let's continue on here. It says, we certainly are not stationary in the universe. Due to the expansion of the universe, nothing can truly be stationary. If increasing speed means time for us slows down, does that mean if we were to decrease our speed, time would speed up? So, for instance, if the Earth were to slow down, would that mean that time itself would speed up for us? If we were to become completely stationary, would we experience the true duration of time? What if time is really just an illusion and the only reason we feel it is because we are moving? What if time is just an effect of velocity, of movement, of speed? What if it's just an effect of that? And if that were true, if we were truly stationary, not moving at all, would that mean that we would be experiencing no time or experiencing ultimate time? Now, what that would look like, I really don't know. That's a mind bender for sure. But it's interesting to think about that time in itself, the way that we experience it, is illusionary. It's at least altered. Whatever time truly is, it's altered by the fact that we are moving through space. So continuing on. In our current experience, 1 second contains about 10 to the 45th power Planck times. So a Planck time, if you're not familiar with that term, we've talked about it on Into the Multiverse plenty of times, but it's the unit of time. It's the smallest amount of time possible. It's the time that a photon takes to travel the Planck length, which is the shortest length possible. Everything in reality is made up of indivisible units, kind of like pixels. There are pixels of space, but there's also pixels of time. Time is more like a flip book or like a film reel of a series of pictures. It's not like a flowing river. It's more like a flip book or a film reel. And the faster these move, it gives that's another way that time is kind of illusionary. Is that really time is the progression of these snapshots. And those units are called Planck time. So in every second there's an unimaginable number of these things. Just like there's an unimaginable number of Planck lengths or Planck units of reality, of physical reality in every square inch. But nevertheless, that's what reality is. So the passage of time is really just the progression of these snapshots. Just like when you put a film in a projector and the projector turns and it whips the pictures through the light source, and then when you watch it projected on a screen, you see a movie. That's actually a really good analogy for how time operates. So it's very strange. So continuing on, if we speed up, the number of Planck times decreases since time moves more slowly for us. If we were to slow down, would the number of Planck times then increase, having the reverse effect, then increasing speed? If we were to decrease our speed relative to the rest of the Earth, would that then mean time would speed up and we would age more rapidly? So would the reverse happen? If we tend to think that when we're on Earth we're stationary, but we're not. We're rotating. The Earth is rotating on its own axis. The Earth is moving around the sun, and all of that. Now, what if you were able to somehow go out into space and decrease your momentum somehow? If you were able to decrease your velocity, would that then mean you would age faster, and then for you maybe a year has passed, but by the time you get back to Earth, it's only like an hour? Would it have the reverse effect? I know it's weird, but it all factors into this question of the expansion of the universe. So continuing on, I believe there is a reason that God has everything in motion throughout the universe. That's not even taking into account the possibility of brains and how fast they might be moving through the bulk. That's extra-dimensional. That's our extra-dimensional material is what we're talking about there. Brains is short for membranes. The bulk is basically hyperspace. Without the perfect balance of motion, speed, expansion, and even gravity, because Einstein also showed gravity has an effect on time, time itself would be very different than we're currently experiencing. Who is not to say the concept of time is different all throughout the universe? Perhaps we live in a reality where things like old Earth creation and young Earth creation can both be accurate. Perhaps it only depends on which side of the coin we are looking at. I, for one, certainly don't know the answers to these questions or fully understand all of the biblical implications. However, I admit, sure is fun to think about. So that's why I wanted to start this conversation with time, because it does. We need the proper understanding of time, and we need to understand that time is relative. Time is not the same everywhere. Time varies depending where you are, how fast you're moving, how much gravity is present. Time it factors in. You got to factor in a lot of things. So time's relative. Time's different. It's amorphous. It's very strange. So we can get into the actual size of the universe. How big is the universe? Now, in the article that we're going to look at, I know that there's a lot of Christians who are young Earth creationists, and they believe that the universe was created 6,000 years ago. That's fine. And there's a lot of old Earth creationists that believe that the Earth was created, 13 or 14 billion years ago. That's fine. Now, in the article that we're going to look at, it's not like it's a scientific article. It's not specifically a Christian article. But I don't think anything in here necessarily has to contradict anything that we believe as Christians, because as I'm going to show you in a little bit, I do believe it's possible you can have both an old and a young view of the age of the universe. It just depends on your perspective. It depends where you're going with it. It depends if you're the one in the spaceship moving at light speed and you're thinking 5 minutes has passed, wherein in reality, back on Earth, that is not moving at light speed, back on Earth, it has been decades perhaps. So I think it's one of those things. So I wanted to look at this article. This is from imagine.gsfc.nasa.gov. The title is the Farthest Visible Reaches of Space. And there's a lot of cool images in here that help explain really what our universe is like from a distance perspective. And it's good to have that framework before we get too much into expansion. But it says, current observations suggest that the universe is about 13.7 billion years old. We know that light takes time to travel, so if we observe an object that is 13 billion light years away, then that light has been traveling towards us for 13 billion years. Essentially, we are seeing that object as it appeared 13 billion years ago. Now, again, I don't want to be so dogmatic on the young Earth, old Earth thing. If you're a young Earth type person, that's fine. Then just place in 6,000 years or something like that, because there are young Earth answers to this question about how do we see. How do we see universe from light years away? That would be a whole other Peck report. I'd be happy to do that. That would actually be a pretty interesting episode if we looked at some of the best evidence of young Earth and some of the best evidence of old Earth or young and old universe, and then kind of compared the two. But that goes outside of our scope for this video. So whatever side you fall on in that argument, just either take it for what it says or just take it with a grain of salt, and don't let that throw you. So it says, with every year that passes, our newest technology enables us to see further and further back. The image used for this stop on our journey is the Hubble Ultra Deep Field UDF. The UDF is one of the deepest views of the visible universe to date. Certainly it was the deepest when it was originally created in 2003 and 2004. There are approximately 10,000 galaxies in this view, right here, which is a sort of core sample of a very narrow patch of sky near the constellation Fornax. The smallest, reddest galaxies in the image, of which are about 100, are amongst the most distant known objects. So, you got some red ones here and here, some over here. The redder they are, they say the further they are because of what's called redshift. It's sort of like, the Doppler effect. When a train goes by, you hear the train, and when it gets closer, you can hear it real loud, but then as it goes away, it sounds like the pitch drops. It goes, like that. Well, the same type of thing happens with light, because light's a spectrum, and the further away something is, it bends and you see more of the red. You see more of a redshift. So it's the same type of thing as the Doppler effect, but they call it redshift. So that's how they measure far away stars and galaxies. Is it perfect? No. There's certainly a lot of issues with it, and some of those we'll look at too, because there's not really a consensus on how fast the universe is expanding, how much it's expanding, or even if it's expanding at all. There's not really a scientific consensus on that. There's lots of physicists that have different ideas. So we will look at those. But first, let's continue on with this. The UDF looks back at approximately 13 billion years, or approximately between 400 and 800 million years after the Big Bang. Galaxies that existed in that time period would be very young and very different in structure and appearance than the grand spirals we see nearby today. So here you see the telescope here, and it kind of shows you on this graph what this thing is able to look at. So according to them, here's the Big Bang. This is the radiation. Having a hard time reading that. That's very small, but the radiation right after the Big Bang. Dark age, first stars. So this ultra deep telescope here is able to see about here, the ultra deep field. It's able to see there. So pretty interesting. That might lead us to the question: what is the furthest known object from Earth? Now this article is a little bit older. This is from 2016, so there might be further objects that have been found more recently. But at least since 2016, this is what it's been able to see. It says here's the newest candidates as of May and September of 2015, respectively. For farthest galaxy ever detected, there's EGS 8P7 at more than 13.2 billion light years away, and EGS ZS 8-1 at 13.1 billion light years away. We don't have to go through this whole thing, but here's an interesting picture. And again, this comes from NASA, but this shows some of the galaxies that it's able to see. It says Hubble provides first consensus of galaxies near cosmic dawn by NASA Blue Shift on Flickr. So that's what that is. Then down here, this was... It says, as of this writing, it seems that one of the galaxies in this recent Hubble discovery may be a distance record breaker. It was observed 380 million years after the Big Bang with a redshift of 11.9. This means the light from this galaxy right here left 13.3 plus billion light years ago. Well, that's, okay, 13.3 years ago. Light years is a measure of distance, not of time. But this is, so... That's this picture. Obviously very blurry and very pixelated because it's very far away. There's some more pictures here of other galaxies and things. Again, we don't have to go through this whole thing. There were just a few points that I really wanted to hit. But if you do want the whole article, you can find that link right up there. Let's see. So here's some more galaxies. Now this one's a simulation of what JWST deep field might look like. Okay, so they put in simulations as well as actual pictures as well, and they tell you which is which. So distance information, and how do we calculate the distance? So this is where it talks about the redshifts that we talked about before, and it gives you some more information on that. This is where it talks about the 13 billion years. And then down here it says, at the rate of 17.3 kilometers a second, the rate Voyager is traveling away from the sun, it would take around that big number, that many years, to reach this distance. At the speed of light, it would take 13 billion years. Now, it says up here, too, scientists have estimated the age of the universe to be 13.73 billion years old, with an uncertainty of about 120 million years. When we observe an object that is 13 billion light years away, we are essentially observing it as it was 13 billion years ago when the universe was young. All right, now, that right there I want to focus in on for a moment, because this question of the expansion of the universe, they say, when they observe objects that are farther away, when they observe galaxies and things that are further away, they're moving faster and faster and faster. So that leads them to say, it leads them to believe that the universe is expanding at an increased rate. Now, what I haven't been able to find is specific mathematics relating time into this whole equation, because when you're looking at a faraway galaxy, you're looking back in time. So why is it not that the expansion of the universe was just faster back then? You know, if you look at, let's say, stars or galaxies or whatever, the further away they are, the faster they're traveling away from each other. I mean, why would that not then just lead to the conclusion that the expansion of the universe was faster before? You know, I mean, you're looking back in time. It takes light that long to reach us. So why would that not be the conclusion? Why would the conclusion be that the universe is expanding faster and faster today? Maybe it's slowing down. Maybe it was faster before, and that's why the further we look out, the faster or the further away we see these objects, or the faster they're moving away from each other, I should say. So that's a question I have. That's something that I don't fully understand why that hasn't been dealt with, or why time doesn't seem to be a factor in, you know, when scientists say that the expansion of the universe is happening at an increased speed. Again, their evidence is they look at faraway galaxies. Well, that's what those galaxies looked like that long ago. You know, if the galaxy is, you know, a billion light years away, well, that's what that galaxy looked like a billion years ago. We don't know that it looks like that today. You know, we don't know that it's traveling that fast today, or if it's that far away from everything else today. So could it be that the expansion of the universe, maybe we got it reversed? Maybe it is actually slowing down. So those are important questions that I don't have the answers to, but I figured, hey, in a show like this, those would be the ones to ask, right? And of course, I encourage all of you to leave a comment in the comment section below and let me know what you think, and let's get a conversation going, because this is really interesting. Now, when it comes to the expansion of the universe, there's several ways to try to understand this, and again, there is no real consensus on how we should understand it or how it really works. There's a lot of different analogies. One that I found really interesting comes from a blog by Jim Pivarsky, and he wrote an article his blog is called Coffee Shop Physics. It's coffeeshopphysics.com if you want to check it out. And I thought he gave a really interesting illustration on what curvature in the universe is all about and how that relates to expansion. So I wanted to go through what he had to say, because he actually relates it to fabric stitching. Now, I don't know how to sew, I don't know how to crochet or anything like that, so some of it's lost on me, but even though I don't know how to do those things, I can understand that a lot easier than I can understand the expansion of the universe. So, of course, I think it's a great analogy. So he tells this story. We can look here. He tells this story at first about how he got into knitting pants and he wasn't that good at it at first, but how this helped him understand general relativity. Excuse me. And he tells. Let's take it from here. Actually, if you want to read the whole article again, the link is up here. But let's take it from here, because I've been confused by this common explanation of general relativity too. A lot of science shows will say that it's kind of like a bed sheet, and you put a ball on the bed sheet with marbles around the edge, and then the marbles roll over close to the ball, and gravity is like that, and that's how space is. But what they don't tell you is that's a two-dimensional representation of a three-dimensional phenomenon. And so I never understood really how that worked. But now that I understand that gravity, it just means that gravity is stronger towards when you're closer to objects, and it actually warps space-time it's sort of in the way that a bed sheet is warped. But again, a bed sheet, we're talking about a two-dimensional surface. You have to apply that to a three-dimensional space, a three-dimensional universe. So it would warp at all points around the object, not just on an imaginary two-dimensional surface. So I'm glad that he brought that up in this article because that always threw me off too. So hopefully we can help explain some of this to other people that might have been confused by that analogy that they've probably heard since middle school science class. But in popular explanations of general relativity, it is common to say that space-time is like a rubber sheet curving under the weight of planets and stars. The planets are marbles that someone has set on the rubber sheet to show that the sheet does, in fact, bend. This explanation has always bothered me because the marbles are outside of the sheet. If the sheet is supposed to represent space, then everything ought to be within the sheet itself. Moreover, the demonstration only works because the real Earth is under the rubber sheet, drawing marbles towards itself. That's right. And it says, and while sheets can be curved, what could it possibly mean for space to be curved? How could I ever visualize that? And I'm really glad that he brought up this concern because I've had that myself. It's always been really hard to visualize it. But I think he gives a much better analogy here. So let's look at this. It says, in school, I learned about the mathematics of curvature and its application to space-time, the theory of gravitation known as general relativity. The formal definition of curvature is based on an intuitive concept, but it is complicated by the subtlety of continuity. Okay, so fabrics approximate continuity with small but not infinitesimal stitches. So in the end, it was the ancient art of shaping cloth with thread that helped me to visualize curved space-time. Video games helped too. How is cloth like space? For this metaphor to work, we have to imagine being a drawing on a cloth. In other words, two-dimensional. I've only ever been two-dimensional in video games, such as the kind where I'm in a dungeon with many rooms. Each room has a north, south, east, and west, but up and down are meaningless. There are doors at the edge of the room. These lead to other rooms, some with hidden treasures or monsters that looked a bit like this. So, if you've ever played any video games, you've probably come across games like this. There is no up or down in this space. There's north, but north isn't up. It's a flat direction. It's not up or down. Not exactly. Just like you can drive down the road north, but you're not traveling up. So it's like that. In a two-dimensional video game space, there is no up or down. It's two-dimensional. So this is a great analogy. It says video games aren't usually projected in cloth, but there's no conceptual reason not to, only technological. Cloth computer screens would be pretty cool. I disagree. That sounds lame, but that's just me. The way the character moves would not be altered by folding the cloth. Adjacent stitches or pixels are still adjacent when the cloth is folded. Our hero would crawl around the crease without realizing that his world isn't spread flat. There's a picture of that here. His world can be changed, however, by how we sew it. Suppose that we sew the east door of the room to the west door. When our hero walks through one door, he finds himself walking in through the other. His whole dungeon appears to be a long east-west corridor of identical rooms. But as you can see here, it's really the same room. Now, his two-dimensional space is curved in his two-dimensional universe is curved in three-dimensional space, but he wouldn't know that. He would travel along, and he would go into the west door and come out the east door. He would go through the east door, come out the west. He could travel around. He might even think that he is in different rooms, but they're all identical, but really it's the same room. He wouldn't realize that he's been curved in the third dimension because up and down has no bearing on his existence. So it's similar to that. Just like our three-dimensional space can be curved, our three-dimensional universe can be curved into a four-dimensional space, and we would not really notice that curve because we're three-dimensional. But things like this could happen. That's actually the whole theory of wormholes. That has a lot to do with it. These kinds of connections can be arbitrarily made in video games. The programmer just needs to type, if exit through west, then enter through east. It's like a hyperlink on a web page. We could imagine something similar in our three-dimensional world without having to visualize it as four-dimensional suture. While there isn't any known way to make wormholes or loop spaces in reality, the idea is all over science fiction, like A Wrinkle in Time. In this article, I'd like to talk about a different kind of connection. A looped space is made from one weird connection. Curvature is made from weird connections all over the place. Suppose that we build a dungeon from a network of linked rooms with 2 north doors for every 1 south door. So you can see that here. And he calls the two north doors, he calls one Ronth and the other Ornth. But these are 2 north doors, and then you have 1 west, 1 east, and 1 south. Now, each step in latitude has twice as many rooms as the previous. I could draw a map of it like this. So here's how you would draw that map. But eventually, these get crowded at the top, right? Now, he says, since the 2 north doors lead in different directions, I'm calling them Ronth and Ornth, the room gets very crowded at the top, so I decided to shrink them in my map, but in reality, these would be the same size. In the world of the video game, they're all the same size. So here's a better way to represent them. So he uses fabric and stitches. These are all these rooms are all the same size, but they're stitched together in this way, and then look what happens up here. It becomes curved. So it says, when these rooms are sewn together, they form a lumpy surface like a lettuce leaf. Our hero doesn't know that. To him, it's just a 2-dimensional world. Because again, up and down are meaningless to him. He's a 2-dimensional creature. So if he was traveling along here, to us, we would see him go up and down, but he would not know that he was going up and down. To him, he would just be going straight. It says, but there are many more places to explore than there are in the normal rectangular dungeon. This is what it means for space to be curved. We say that the cloth is curved because it cannot be laid flat due to the way that it's stitched. This is something more than merely folding a normal sheet of cloth. A curved cloth cannot be made uncurved without cutting or stretching. The 2-dimensional space corresponding to that cloth is also curved. To make the correspondence explicit, imagine a computer screen pixel for every stitch in the fabric. The essence of curvature is the way that pixels, or points in space, are connected to each other. And a point in space is that Planck unit that we talked about. It's a Planck length in 3 directions. It's a Planck length. A Planck length, by definition, it's a sphere of Planck length, and that it's a point in space. So imagine that as a pixel. You could imagine a pixel as stitches in the fabric. So it says, again, the essence of curvature is the way that pixels or points in space are connected to each other. Despite his 2-dimensionalness, the video game character knows that his world is curved. One experiment he can do is to measure the length of the path between 2 points. So you have path A here, and you have from A to B here, the top one, and then you have the bottom one. Now, I'm going to leave this picture up so you can look at it while we continue here. I'll try to. In an uncurved space, the shortest path between 2 rooms at the same latitude is a straight line east to west. To get from room A to B, we might imagine that the shortest way would be to go east, 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 7 rooms. So straight line. But in this space, south, south, east, Ornth, Ornth is shorter, 5 rooms. So this way, not a straight line, is shorter than this way, which is a straight line. Isn't that strange? And it's because his space is curved. Even our video game hero, this does not seem to be a straight path. First he's going south, then he's going Ornth, but it is undeniably shorter. Breadcrumbs prove it. Experiments like this measure the degree of curvature. If the shortest path appears to be very curved, then the space curvature must be very large. In an uncurved space, curvature equals 0. The shortest paths are perfectly straight lines. In a positively curved space, such as the surface of a globe, the shortest paths are great arcs. Airplanes fly over Iceland on their way from Chicago to Switzerland. The video game space we've been considering here is negatively curved, and if we have 3 north doors for every south door, then it would be more negatively curved. All right, so he gets into more stuff in here having to do with time and extra dimensions and things like that. I want to skip past that and read the last paragraph because or the last part here, because I think that this is just kind of an interesting thought experiment, and it has to do with our conversation about time and the expansion of the universe. So you could think of that expansion and the curvature of space as those frills at the end of the fabric. But let's take it from here. The curvature that causes a flying arc through the air to be shorter space-time path than just staying on the ground is an extremely small one. Our space-time is very nearly flat. On the second floor of a building, time intervals are only 1 part in a quadrillion longer than they are on the first floor. For a GPS satellite in orbit, an hour and 1 microsecond passes for every hour on the ground, and they need to be routinely synchronized to correct for this. So that's similar to the experiment that we talked about the atomic clocks and planes and stuff. This tiny curvature is only noticeable to us because we have a foreshortened perception of time. Now, this is where it gets interesting. It takes billions of nanoseconds, that is, a few seconds, to see the path of a tossed object deflect a few feet. Though the Earth's gravitational curvature is tiny, we are sensitive to the passage of time at exactly the right rate to be aware of it. It makes me wonder if this is a biological adaptation to living on Earth, much like the fact that we can only see the colors of light that can penetrate Earth's atmosphere. Would creatures that evolve in low-gravity environments, such as asteroids, sense time much more slowly than us? Would creatures in high gravity, the cool husk of an ancient white dwarf star, seem to live at a maniacal pace? And, set aside all the evolution stuff, but it begs the question, time is relative, so would it be different for us or any creatures if they lived on an environment with stronger gravity? And we know that it would be different because of black holes. We know that as you approach a black hole, time operates very different for you. Actually, that's why you can never reach the epicenter of the black hole, because time would be moving so different for you that to you, the outside time in the rest of the universe would speed up so fast, you would see the end of the universe before you would reach the center of the black hole, which is really weird, but that's what would happen. So let's continue on. Talking about expansion, there's this question, why aren't we expanding? If the universe is expanding, why don't we see the Earth expanding? Why aren't particles expanding? And I thought this was a great article for this. So let's take a look. This comes from Forbes, but it says if you take a look at almost any galaxy in the universe, and you'll find that it's moving away from us. The further away it is, the faster it appears to recede. As light travels through the universe, it gets shifted to longer and redder wavelengths, as though the fabric of space itself is being stretched. At the largest distances, galaxies are being pushed away so rapidly by this expanding universe that no signals we could possibly send will ever reach them, even at the speed of light. Okay, but again, right there, at the largest distances, galaxies that are the most far away as they can be from us, galaxies are being pushed away so rapidly by this expanding universe. But again, when you're looking at galaxies that far away, you're looking back in time. So if you're seeing them being pushed away incredibly fast, why is it not that they were moving faster back then, but they're not moving as fast now? So why is it that the expansion of the universe is increasing and not decreasing? Let's say God inspired a Big Bang. He snapped his fingers and there's a Big Bang. Wouldn't we expect all that stuff that flew out from that, just generally speaking, to slow down over time? How could it be that it's speeding up? So that's my question. But anyway, let's continue. It says, but even though the fabric of space is expanding throughout the universe, everywhere and in all directions, we aren't. Our atoms remain the same size. So do the planets, moons, and stars, as well as the distance separating them. Even the galaxies in our local group aren't expanding away from each other. They're gravitating towards one another instead. Here's the key to understanding what is and isn't expanding our expanding universe. So this is the original concept of space, just a grid, basically. And there's some interesting history behind that, how this was originally what the universe was thought to be like. Then Einstein came along. He had a theory kind of more akin to this. But again, this grid is a two-dimensional surface. The two-dimensional grid is only meant to represent three-dimensional space. So really, this grid would be all around this sun and this planet. So Einstein came along and developed that. But this explains that. So this talks about static universe. Now this graphic right here shows now how people understand the expanding universe. So they usually use a loaf of raisin bread to explain it. As the loaf expands, the distance between the raisins expand too. But again, even there's no reason that expansion would be faster and faster and faster. That doesn't make sense. Yet that's what a lot of them claim. So this says the mathematics tells you about the possible solutions, but you need to look at the physical universe to find which one of these describes us. That came in the 1920s thanks to the work of Edwin Hubble. Hubble was the first to discover that individual stars could be measured in other galaxies, determining their distance. Nearly concurrent with this was the work of Vesto Silfer. Atoms work the same everywhere in the universe. They absorb and emit light at certain specific frequencies, which depend on how their electrons are excited or de-excited. When he viewed these distant objects, which we now know to be other galaxies, their atomic signatures were shifted to longer wavelengths than could be explained. And then they combine these observations. And if you want, you can look at the article to get all of this stuff. But the way that it's explained is that there are two ways to make sense of this phenomenon that we see. First, either all of relativity is wrong. We are at the center of our universe, and everything was moving symmetrically away from us. It's one possibility. I don't have a reason to believe in that, but I also don't have a reason to throw that out. That what if we are in the center, and what if that's what we're looking at? That would account for some of this. But again, I don't have any evidence or any real reason to believe that. It's interesting to think about, but or number two, relativity was right. Friedman was right, and the farther away a galaxy was from us, on average, the faster it appeared to recede from our perspective. So it says here, we'll take it from this paragraph, the further away an object is from another, the more stretching occurs. Now, it's interesting that they use stretching because there's a Bible verse that talks about how God stretches the heavens like a tent. Now, imagine there's one point on that tent, you put, like a piece of rubber or something, and you stretch it. Well, at all points on that rubber, the ones closer to the bottom where you're stretching, they're going to get further away. And it's going to appear to be faster. Now, it's going to appear to be. It wouldn't necessarily have to be faster, but it would appear that way because space itself is getting stretched. One way you could think of it is if you have, let's say, a yo-yo, and you have it on a long string, and you're spinning it around, and you're slowly letting the string go. So the yo-yo is spinning, and it's slowly being let out, having wider orbits until eventually it is released from your hand and it goes and flings out into the distance. Well, imagine that same thing, but imagine you're rotating with the yo-yo. So as you're spinning it, you're looking at the yo-yo and you're rotating with it. Now, as you're rotating with the yo-yo, let's say that you're only looking at the yo-yo and all you see is the distance between the yo-yo and you is increasing. You're not taking into account the spinning, the orbit. From your perspective, it's going out, but it seems to be receding from you faster and faster until it flings out because you let it go. It's not actually going faster, but it appears as if it is because you're not taking the rotation, the orbit into account. So it seems like the further it goes out, the faster it's moving. What if something like that is going on? What if the only reason it seems like it's moving faster is because we're not taking into account four-dimensional space that our universe might be rotating or revolving through? And if space-time is curved, it would stand to reason it must have a higher dimensional space to curve into. Just like if two-dimensional space was all there is, you can't curve a piece of paper because what are you curving it into? You would have to have a third dimension to curve it into. If space-time is curved, you need another dimension for it to curve into. So it's interesting that they use the analogy of stretching because the Bible uses that analogy or that literal fact, depending how you look at that verse. They use that as well in the Bible. So it says, if all you had was a universe filled uniformly and evenly with matter, that matter would simply get less dense and would see everything expand away, everything else as time went on. And then this has to do with the cosmic background radiation. It is a factor into this, but it would take a long time to go through. But it says, but the universe isn't perfectly even and uniform. It has overdense regions like planets, stars, galaxies, so on and so forth. So things are different. Now here it shows cosmic epochs. So this is present time on this side. Here's the telescope, present time. Now, as they look back and back and back, they see that these objects are moving faster and further away from each other. But again, this is back in time. So back then they were moving faster. That doesn't mean that they are now. And actually, there's no reason to think that they are now, because when we look at objects closer to us, they're not moving as fast away from us as the further ones. So why is it not that we got this whole thing flipped? That we made a mistake somewhere and forgot to factor time into it, and actually the expansion of the universe is decreasing. So this goes on to say, because the question of this is why space expands and the objects in space don't. Why the expansion of space doesn't have much to do with like the distance between the Earth and the Moon. And what they really talk about here is that other forces come into play. So if the force of gravity is stronger than the force of the expansion of space, then gravity wins and there is no expansion between those two objects, say, the Earth and the Sun, for example. Then there's no expansion because gravity is a stronger force. You have other forces that could play into it as well, radiation, things like that. So there are certain localized areas where the expansion doesn't occur like that, because again, gravity wins. Now, could that be because now the expansion force, the initial thrust of the Big Bang, say God snapping his fingers or God speaking everything into existence and everything flying out, could it be that now, because entropy has taken place over a longer period of time, things are slowing down more than they did before, and now gravity can overcome the expansion of the universe? Could it be that that's all it is? I don't know. So that's this article. There's a lot more great information here if you want to look into it. Again, it's at Forbes.com, and the title is "This is Why We Aren't Expanding Even If the Universe Is." Now I want to move into something, and we'll keep this one brief, but I want to move into something that shows that this question of the expanding of the universe, there is no consensus on it. And it's looking like now they might have got some of their numbers wrong. So at space.com, there's a headline that the universe is expanding so fast that we might need new physics to explain it. I don't want to spend a lot of time on this because it's really just to prove the point that no one really knows. So this is a big mystery. It's a big question, and there's not a consensus. There's a lot of different ways to look at it. So apparently, as the article says, the universe is expanding faster than expected, suggesting that astronomers may have to incorporate some new physics into their theories of how the cosmos work. The new study reports. The revised expansion rate is about 10% faster than that predicted by observations of the universe's trajectory shortly after the Big Bang, according to this new research. The study also significantly reduces the probability that this disparity is a coincidence from 1 in 3,000 to just 1 in 100,000. So Adam Rees, professor of physics and astronomy at the Johns Hopkins University of Baltimore, says in a statement, quote, "This mismatch has been growing and now reached a point that is really impossible to dismiss as a fluke," end quote. Now, he also said, quote, "This is not what we expected," end quote. And he won the Nobel Prize for Physics in 2011 for showing in the 90s that the universe's expansion is accelerating. So he was one of these. It's unclear what's driving this acceleration or apparent acceleration, but many astronomers say that it's dark energy. And we haven't really got into dark energy yet in this video, but we have talked about it a lot. So their explanation is, well, it's some mysterious energy that's doing it. We don't know what it is, so let's call it dark energy. And that's really about all they know. But again, it might not be that. It could just be an illusion. It could be an illusion due to the relativity of time. It could have something to do with that. But this is just to show that there isn't a consensus on how fast that it's expanding. Even more than that, there's another article here that we can look at that there's not even a consensus that it's expanding at all. So some physicists say that the universe is not expanding at an accelerated rate. There were 3 astronomers that were awarded the Nobel Prize. Okay, so we talked about that already, about this accelerating rate thing. But there are some now that don't believe that it's expanding at an accelerated rate, that it is expanding, but it's not accelerating. The expansion isn't accelerating, it's decelerating. So a Royal Swedish Academy, as the Royal Swedish Academy explained on the morning of the Nobel Prize announcement in Stockholm, in a universe which is dominated by matter, one would expect gravity eventually should make the expansion slow down. Imagine then the utter astonishment when the groups of scientists discovered that the expansion was not slowing down but was actually accelerating. All right, so that's like basically what was discovered. But now an international team of physicists have questioned the acceleration of the universe's expansion because they have a lot bigger database of type 1a supernovae, which are used to measure the acceleration of the expansion of the universe. Now there's a much bigger database than what was available in the 90s when this was first done. So they've been applying it, and this team has said that they've been able to account for the subtle differences between them like never before. And it goes on to say that they actually believe that it's not accelerating, that the evidence for accelerated expansion is at most what physicists call 3 sigma, which is far short of the 5 sigma standard required to claim a discovery. So everything in science is based on statistics and things like that. So statistically something is true, and they need a high percentage of statistical probability to call something a discovery, and they base that in sigma. So if you have read my book, Abaddon Ascending, you already know all of this. If not, you can get the book and you can learn about it there. But if they discover, let's say they have a 3 sigma amount of statistical probability that a particle exists, they would not call that a discovery of a new particle. They need a 5 sigma. So what they're saying is the idea that the universe is expanding at an accelerated rate is only 3 sigma. So that should not be counted as a discovery. Now, they're going to do more research into it, and they're going to look into it, and we'll have to wait and see. And of course, we will stay on top of that story here on Into the Multiverse. But it just goes to show that there is no consensus that the universe is expanding at an accelerated rate, or even what that accelerated rate would be. And this brings us to this article that I wanted to look at, and then we'll close out. Time is actually slowing down and will come to a halt, says a radical theory. Now, this is something that actually says maybe the expansion of the universe is an illusion due to time itself slowing down. That it's not actually accelerating, but time itself is slowing down. It says, if you think about it, time can really weird you out. What is it exactly? How do we know even real, that it's even real and not a concoction of our brain, so on and so forth. One team of scientists looked at time from a different perspective. They considered the fact that the universe appears to be speeding up in its expansion and wondered, what if that's not really happening? What if instead time is actually slowing down? Not only that, one day it might come to a complete halt. In other words, time might actually end. There is a Bible verse in Revelation that says that at some point time will be no more. We don't know how literally we can take that or what exactly it means, but I did talk about it in Abaddon Ascending, and it has to, the way that I talked about it there kind of has to do with this. Continuing on, the idea came to Professor Jose Senovilla and colleagues Mark Mars and Raul Vera of the University of Basque County, Bilbao at the University of Salamanca. They thought that rather than supernovae moving away from us, indicating that the universe's expansion is speeding up, we are not actually getting farther from anything, but time is slowing down, so the light is taking longer to reach us. There is no mysterious dark energy under their theory either. They say, quote, we do not say the expansion of the universe itself is an illusion. What we say may be an illusion is the acceleration of this expansion. That is, the possibility that the expansion is and has been increasing its rate. So it says, what will happen once time stops altogether, perhaps in billions of years from now? Then everything will be frozen like a snapshot of one instant forever, explained Senevilla. More specifically, in the paper that they published, the scientists propose a theory that sees our universe being made or being inside a multidimensional brain that floats through a higher dimension of space. And again, like I said before, if space-time is curved, it's got to curve into something, so it makes sense that there is higher dimensional space for it to curve into. Time under this theory is the fourth dimension that's slowly degrading into a new spatial dimension, which is kind of interesting to think about. It goes back to the very beginning of this whole episode, that what if time is just a type of space? And that's kind of what they get into here. Now, as we talked about before, it's really difficult to talk about how old the universe is or how fast everything happened because it depends on your perspective. Let's say the Big Bang happened, God spoke, everything flew out, and expanded. If you are a particle that's flying out and expanding, to you, it could be, let's say, 6,000 years. But to everything else outside of that particle, it could be billions of years. It's the same concept that has been proven to be true that says the faster you move, the slower time moves for you. So if you're in a spaceship and you're traveling close to the speed of light, you're moving a lot faster. For you, it might only be a few days. Back on Earth, the outside universe, the part that's not moving as fast as you, it could be several hundred years, depending on your velocity. So it could be that in reality, everything could have been created in 6,000 years if you take that perspective of the things that are moving. But really, the universe, from an outside perspective, is 13 or 14 billion years old. This weird time dilation effect has been proven to be true. Time is relative. So it could be that both the young earthers and the old earthers, or the young universers and the old universers, it could be that they're both correct. They're just looking at it from two different sides of the same coin. And that to me is really interesting. Really interesting. So if you wanted to look at the rest of this article, you could do so. It's at bigthink.com. There is more to it, but I think that it's interesting that time itself could be slowing down, and that would factor into all of this as well. If time itself can degrade, if time itself is subject to entropy and it can slow down and wear out, what would that mean for the rest of us? What would that mean for Bible prophecy even? So that's another interesting aspect of this whole thing having to do with time and the expansion of the universe. Okay, let's see how we're doing on time. I think we're about out of time here. So let's. There are some things that I want to ask you at home. Some questions that I have for the audience. Question for the audience time. Now, I want to know, in your opinion, is the universe expanding? And if not, what is really going on? What is the cause for this illusion that the universe is expanding? Or do the scientists have it right, and is it actually expanding? I also want to ask you, do you believe that dark energy exists? And if so, what is it? So do you believe that there is this mysterious energy causing space to not only expand, but expand at an accelerated rate? What is dark energy? What do you think it is? What are your theories? I would like to know. And lastly, could dark matter be connected to dark energy in some way? What do you think dark matter is? What do you think dark energy is? And could they be connected? Could they be two sides of one coin? I want to know your theories. Please leave me a comment in the comment section below, and I would love it if you guys would have conversation amongst yourselves too. I'll be looking at the comments. I typically do because I love reading your theories. You guys are super smart, and I love having conversations with you about this kind of stuff. So I want to know what you at home think about these questions. Please leave a comment in the comment section below. While you're there, make sure you share this video, subscribe to this channel, click the bell for notifications. You got to click the bell to get notifications. And if YouTube doesn't notify you, just know that every Thursday morning at 9 a.m. Central, you will get a brand new episode of Into the Multiverse. All right, all that being said, fantastic discussion, some really cool things to think about. You probably won't be sleeping tonight. I know I won't, because I'm going to be thinking about higher dimensional space and time dilation. But so you're welcome for that. But I want to thank you all for watching Into the Multiverse, which, as you know, is the show that dares to expose the hidden truths that the world wants to keep secret and the church would rather ignore. Thank you so much. Until next time, take care and God bless.
When did the government alien programs originate and why? Who were the Collins elite, and were they exposing the dangers of such programs? What exactly did these black projects involve? Learn the astonishing answers to those questions and so much more. Skywatch TV is proud to announce the Higher Entities Ultra Collection. This special offer includes the new Fall Brothers feature film, Higher Entities, The Lost Tapes, which is a live-action documentary including up-close and personal discussions with former FBI agents, Department of Defense consultants, best-selling authors, and seasoned research professionals that deliver intimate testimonies of disclosure, which put you face-to-face on location and in the conversation, featuring Justin Fall, Dr. Thomas Horn, Ray Boucher, Derek Gilbert, Stan Deo, Darren Geisinger, Chad Riley, and Wes Fall. But that's not all. You'll also receive the top-secret 5-volume DVD collection, Project Stargate. This unprecedented series of never-before-released confidential interviews features 12 of the world's leading authorities on UFOs, so-called aliens, gods, and the coming day of contact. You'll be amazed as we go behind the scenes to ask experts what they really believe is coming. Watch as men with security clearances like the late Dr. Chuck Missler share for the first time what they know. Then take notes as Dr. Michael Heiser, the late Chris Putnam, Russ Dizdar, Joe Jordan, L.A. Marzulli, Daryl Sims, Gary Stearman, Joyce Aarons, and others as they weigh in on what will soon cause the world to stand still in awe. Project Stargate holds a retail value all by itself of $150, included now for a limited time in the Higher Entities Ultra Collection. Sold separately, this Ultra Collection holds a retail value of $175. Yours now for your donation of only $35 plus shipping and handling. So take advantage of this incredible offer now and receive all 5 Project Stargate DVDs along with the new Higher Entities documentary for your donation of only $35 plus shipping and handling. Now at the Skywatch TV store. Order the Higher Entities Ultra Collection online or call 1-844-750-4985.